MedBricks webcast is a new kind of healthcare media channel to break the silo mentality and foster interdisciplinary thinking. Our mission is to fill that gap and to create a curiosity through different lenses, tapping the passion that guided the historical figures in medicine and bringing present-day groundbreaking research to the front lines. We interview physicians and leaders in the industry about present-day healthcare challenges on our live programming. Welcome. This is Ramana. Welcome. This is Ramana Hanumaraju, the MedBricks host of the MedBricks webcast. We are. I'm not Albert Einstein, but I'm pretty good. But my guest is much more pretty good. So I'm also going to join with my co-host Dola Shahi. Dola Shahi. She told me to pronounce her last name very good. So I'm trying my best. So my guest, Dr. Asha Pillai, is a Stanford and Harvard educated woman. She is having a little bit of problems getting into the system. She is trying in different ways. I hope she's going to join soon. Okay. So let me bring my co-host. I can chat with her a little bit. Welcome, Sheila Dola Shahi.
Very good.
Did I say that?
Okay. Yes, you did a great job.
So tell me, while she is, our guest is having a lot of problems, she's calling me and saying that, and she's trying to get into a hard time getting into the system. It is she cannot get through the. That's why I clearly mentioned about laptop. It's my system is extremely demanding video system. It is audio and video qualities has to be very good. They have to use the Chrome browser. They have to use a little restrictions there. So sometimes the guests are having a problem. If you use iPhone, is a problem. It's not really good. So she's still trying to get into the system. Let me just give me while you talk. Why don't you talk something about your book, your father, a little bit while I'm doing that, talking with her to get into the system, Sheila.
Yes, I'm happy to do that. So, as Ramana mentioned, I am co-hosting with Ramana, and I've had a pleasure of meeting Ramana when I was invited as a guest, actually. The guest that wouldn't leave, so I'm now the co-host. But I just published a book, and it is a tribute to my father. It's called Pack Your Own Healthcare Parachute, A Physician's Death Through His Daughter's Eyes. And it's not only a tribute to the way my father used to practice medicine, which was noble in itself, but when he became a patient, the medical system had changed so much that he needed a village to advocate for him as a patient. And throughout his journey of his illness and sad passing, we learned so many lessons, and I thought that those would be valuable lessons to share in a book, and hence the publication. So you can get it on Amazon. If you can spell my name, you can find the book on Amazon, Ramana.
Oh, very good. So why don't you talk about your what is the book about a little bit?
Yeah, sure. I talk about why you have to advocate for a loved one. And I've been getting involved in lots of patient organizations, patient advocacy organizations of late. And there are really so many things that I talk about in the book in terms of why you need an advocate. Because starting with, healthcare proxy, and walking through the decision steps along the way, and needing more information and someone to untangle all the data for you. There's really so many steps involved in managing or navigating issues, particularly when it comes to the hospital, that you definitely need someone, a family member, or even better yet, a patient professional patient advocate who can be very objective and who can help along the way without having any kind of allegiance to a particular hospital or be paid by any specific organization, so that they are as neutral as possible of a party and can help advocate what's best step to be taken for the patient.
So Sheila is Asha is online. I don't know whether
Yes,
she can hear us or she
I
can
can.
talk. You can hear us?
wonderful.
Hi, Sheila. Nice to meet you. I saw your last interview with Ramana, so
Uh,
wonderful. And it's really great to hear your story and
Oh,
your.
thank you. Oh my goodness, that means so much coming from
it
you.
is truly an honor, Sheila.
Oh, no.
It's an honor, Asha. You know, Asha and Sheila, they all sound similar, right? So,
No. Let me not
Asha,
interrupt you. I
I
wanted
see,
to
I
hear what
follow
you had.
you on the LinkedIn
I'm
here.
so sorry. I had a problem connecting. I hope you can hear clearly.
We can hear you clear. Thank God it's working out.
Okay, very.
Aisha, you know that. Let me hand over to this one. She's gonna. So tell me. I know I promoted you. You're Stanford educated, Harvard educated. Your qualifications are impeccable credentials you have, and you're now
Thank you.
running the cancer division of the Regeneron. It's really your prestigious person to be. You know, I am. I from the you post a lot of Indian related stuff. I thought you were going to enjoy this my show, also presentation of the Indian Nobel Prize winners, so many of them from Kerala. So that's why I thought that would be good. So let me hand over to Sheila to introduce you, and
Okay.
I can do some interview, some
Oh,
questions.
wonderful. That's
Okay,
wonderful.
Sheila, go ahead. Talk
Yes,
with her. She is the right
Asha,
person
I
to.
was just reading a little bit about you, and I particularly loved the like that you had for something that came through on LinkedIn, which was let us compete with science, not with each other or other people in science. I was really moved by that. I was also moved by your philosophy of leadership, and your attention to ethics. I just have so many questions for you, but let's just start out with a couple. If you
Sure.
can just bring us along your journey, your scientific journey thus far, and just give the audience a little bit of a feel for where you've started from and where you are now.
Certainly. So I know that Ramana mentioned my post related to India. I would actually say that it's much more related to discovery, knowledge, and truth, and that's really, I would post just as much about any other uh, historic group, etc. It's simply that I'm most familiar with my background, of course. I emigrated to the U.S. when I was 4 years old with my father, who was a sort of premier physicist under a very well-known. Ramana will know of him. His name was Homi Bhabha. He was one of the premier nuclear scientists of India. He was actually um, uh, an academic and visionary leader of India right after independence. And so my father came here for his graduate study and for developing of education for his children and other things of that nature, which were pretty typical of the incoming generation of that period. Um, and I grew up around the United States. So we started in Wisconsin, Madison, Wisconsin, Chicago, Illinois, my father then moved from Loyola University, where he was a physicist practicing in cancer, the safety aspects of radiation therapy for cancer. The physicists are the unrecognized forces that sort of um, maintain the safety of patients, and they're the unrecognized, unrequited people who truly drive the therapies in those spaces, along with a clinician who specializes in that area. So he then decided to move back to get his PhD, and we relocated to San Antonio, Texas, um, where he received his PhD. So I did my elementary school there in the public school system there, which was fantastic. And my father then received his first job after his PhD at UCSF, University of California, San Francisco. So we relocated to the Bay Area at a time just actually 8 to 10 years before the IT boom, when there was literally a very nuclear group of very few Indian families in the Bay Area. So our family and things that I did also were very active in establishing a lot of the things that are sort of well understood and known among the Indian community there. So, temples and arts groups and various newspaper, and magazine systems and all those sorts of things. So I was very active in the sort of South Asian um, cultural scene, but mainly because I was so fascinated by Vedic or Vedantic ancient Indian culture and history and science. And so around this time, my father then received a second job in Albuquerque, New Mexico, and we moved there. And that's when I started research actually in laboratories and became very fascinated with immunology, which is the study of the immune system, and blood disorders. And so I then started research in those areas. My sister had a really devastating anaphylactic, which is a severe allergic reaction, when she was 10 years old and was in a coma for 87 days. And we had a lot of family experiences around her recovery, which has been very 30 plus years of recovery, et cetera. She's luckily neurologically fully intact, except that she has problems with her vision and her balance. And so I think, because this is an immune reaction that set this up, it even furthered my passion for research that's curative and things that have to do with immunology, which is why I bring it up. And so right around then, I was making big decisions about scholarships and other opportunities I had to go to major universities versus being at home with the situation that we had. And my sister was the person who really, as soon as she could speak, she was very adamant that, you have to go and continue your training and do what you plan to do, and just always do it for me. And, so I have a different perspective. And I understood when you were talking about your father and, the family situations that bring us into a space. I've now resuscitated so many people in intensive care units, and I understand the psychology of the space very well as having been a family member there. It was difficult to peel my mother away from the bedside, and so around that time, I made a decision that I was very interested in continuing to do discovery-based science that would really influence cures for children with blood disorders, and this is how all of these things sort of came together as a mission for me. I think I always planned to do this regardless in terms of my passion for science. I also was very enamored of going back to India and doing service, and so I helped start some hospital systems in India that are pretty well established now, drew floor plans and was involved in all that at a time when it wasn't considered very realistic to think about those things. And now these are major systems that people routinely utilize, that have become major places for people to go back and serve. We're reversing brain drain in the country. So there are many experiences from those things that have helped me to form who I am and my views on development, service, ethics and integrity, and science as a force in society. So there's a lot of things that tie in there. And around this time, I went back to Stanford to do my undergraduate training in immunology, and was also very involved in, as I mentioned, going back to the cultural scene, and things that we had established 6 years before in the Bay Area. And so what happened then was, we were there before the IT boom, but in this period in between, right after, we were the first beta test group for Steve Jobs and the Apple group and the Microsoft groups in terms of cluster computing and all of these things.
Mm-hmm.
Right after we left our undergraduate training, many of my colleagues went into different areas of IT. They became entrepreneurs. I know several people who are well known in the IT entrepreneurial space. I won't name them here, but very well established, with people know very well. And so the entire landscape of the Bay Area changed right after that. It's a very different environment than what we grew up in. So when I came back to do my fellowship training, which is advanced clinical training, I developed a training program that allowed me to take care of both adults and children, but it wasn't really in place at that time. So I had to develop that. shortly after we started that, and Stanford was very excited about it and very supportive, as were a few other major centers. I chose Stanford again because of my connections there with the hospital systems in India. All the things I'm passionate about were centered there. So I came back from my training, began doing some significant benchtop research, which is basic research in immune system differences that have to do with how we can make better transplants. And one of the things that I helped discover was a pathway through which it's actually a part of the process of um, immune protection in pregnancy, but it's also very important for a type of transplant that we helped innovate, which is being able to transplant people from people who aren't matched to them. And so, traditionally, these kinds of transplants were very restricted by people having to be matched to each other, and that
Sure.
puts most of the world in a great disadvantage, because that means only really Caucasian individuals who are in the donor registries can donate for those patients. And so it was unheard of to be able to transplant, an African child or an Asian child easily from a mismatched donor, such as a parent, for example. And so we helped develop that field shortly thereafter. There are many other groups that were involved as well, but I was something that I was very focused on. And shortly thereafter, I was recruited by St. Jude Children's Hospital with my National Institutes of Health funding to start my laboratory program. Went to Memphis, Tennessee, where we started serving the children there, and realized very quickly that we could do these mismatched transplants even better in children than in older adults, which is what I had started a bit at Stanford. And so we've since moved that field forward. And one of my goals now is to be able to bring that allows more than 90% of children to have cures from their parents. And this really took away a lot of the potentials of healthcare disparities. I don't want to say we've solved it, because there's still complications that we have to be careful about. And we just want to make these more and more and more safe. So my coming to Regeneron was really part of an effort toward that. And there's a very large oncology group here. I'm just one part of it, but I have a role of a scientific advisor to the programs in blood disorders and transplantation. So I hope I gave you a sort of overview of.
Wonderfully inspirational story with your father and your sister, and how you've continued to forge new paths ahead for the betterment of patients. And I'm just really touched and in awe of what you've done. You talked a little bit about transplantation and, minimizing rejection when it comes
Right,
from
exactly.
a non-matched donor. So I'm very interested if that is sort of what you're referring to as innate immunity, and how that plays a role in it. And for, maybe layman's terms, if you could just explain a little bit about that, that would be wonderful.
I mean, you didn't need me to do it. You just summarized it beautifully. So, so if I were to summarize in a little bit more, detail, although I really think you did a fantastic job there.
Thank you.
Innate immunity. All of us have innate immunity, and we have another type of immunity called adaptive immunity. And it's sort of we could call it a bit of an arbitrary distinction, but it's actually very important for a reason. So everything about your innate, when we talk about innate, we think of what's natural to us, correct? Your innate talents, your innate beauty, your innate voice, and so on. And so adaptive gives the sense of changing to mold towards something, adapting, right? Changing
Right.
according to a situation. And indeed, that's a very good description of what these two parts of our immune system do. So the innate immune system naturally responds very quickly and efficiently to new threats. And, I trained several graduate students and postdoctoral fellows, which is the next level past a PhD, in my laboratory program. I always am such a a nerd for the immunology of it, and I would go through all of these things with people and say, for example, the reason we have an innate immune system is to be able to respond to a new pathogen that has never been seen before, like, for example, a virus. And I have literally been teaching that for over a decade and a half when COVID broke out.
Right.
And this is an exact example of what we're talking about. Innate immunity is extremely important for responses to those pathogens. So also is adaptive immunity, but it takes more time to develop. Therefore, when you have an immediate threat to life, I mean, the innate immune system is very central to that. There are other aspects that have to do with that innateness, that naturalness. And one of those is that it's not restricted in its responses as much. It's much more widespread in its response. For the same reason, and a good example is if you have a wound or you have something that penetrates your skin, you'll have a pus response or a cut. And that pus response is the innate immune system dominantly responding.
Got it.
And after you've had that response to the same thing, for example, a virus that's coming through your nose, you'll have that sort of very inflamed immediate response. The T cells, which are another part of your immune system, part of the adaptive immune system, will come in. And you've heard about CAR T cells and immunotherapy. These are all things that we were actually involved with in the earlier days of developing those things. Not the CAR T, but the development of the CAR and how it's used for immunotherapy. And so one of my mentors was actually the person who developed that. And so this system is designed not to respond immediately, to sit back, learn what is going on, study carefully which areas of that invader need to be targeted, and specifically target that, and have a very highly precise and repetitive but specific, very narrow response. So it's a very different type of response. The beauty of it is not only that it's specific and narrow, but it's repetitive. And that is the type of part of the immune system that we activate when we give, for example, immunizations. The goal is that you give a challenge, the immune system develops these adaptive cells that have memory. They have the ability to come back. And then when re-challenged with the actual invading organism or thing, they will respond very specifically. So I like to call the T cells and the adaptive immune system something of the Navy SEALs of the system. And the innate immune system is like the massive soldier response.
Analogy.
Yeah, so you don't want to call in the Navy SEALs for everything. And they should have very targeted, very specific missions. And they know their mission very specifically. But they take time to be able to do that very well. And they only are a limited number of
them available
individuals that can do that. Correct. So that's essentially it's very similar in many other ways to that analogy. The T cells have a very limited type of response. They die off after they do their work. They get exhausted from the work, and so on and so forth, which is very much like the Navy SEAL analogy, whereas the innate immune system is the workhorse of the system. So coming back to that, I thought about harnessing the innate immune system to develop the type of transplant, which wasn't the focus. It was always this narrow part of the immune system that everyone was focused on. And I trained with the people who helped discover T cells and all of these things when I was at Stanford and as an undergraduate. So I understood very well why this paradigm was so dogmatically shifted in this narrow direction, ironically. Right. And so I was very interested in opening it up to a very different way of thinking about the problem. And there's a type of half-match transplant that every woman has multiple times in their lives if they have multiple children, and that is pregnancy, because only half of the genes of the fetus or the baby are related to the mother.
That's
the other half. Right. So it's a perfect example of that type of transplant, right?
How we have adaptive.
You have the adaptive and the innate.
The capability.
Correct, exactly. And so I was interested in harnessing the innate capacity of the immune system to prevent those reactions across these immune barriers. And that's what we found. It took a lot of mouse research and a lot of details and a few extra years of committed work at Stanford when, things were much easier to go a straightforward direction with the degrees and the other work into clinical cancer treatment and transplant. But this was really worth it because it helped us to make some breakthroughs in the space and really change the way we think about transplantation and how it can be done. And ironically, even though, as I say in my LinkedIn profile, I've always been interested in equity, diversity, and all these other things from a personal and social standpoint. That wasn't the center of my research work, but it happened that we solved a problem that literally is in the center of that. So global access to transplant cures for sickle cell disease, thalassemia, the most common blood conditions worldwide, is made possible when you have the access to a free donor who is your parent. And you'll be very hard pressed to find a parent who's not willing to donate their blood or their bone marrow to save their child.
Exactly.
So we
Amazing.
actually we took away a lot of the cost aspects of that by also simplifying the transplant in a way that it's less toxic, and therefore the patients don't have to be in the hospital in such severe reactions and complications. So that also brings the cost of a transplant down. And when I went to Miami, I moved there from St. Jude, when we realized that this major centers for these kinds of blood disorders, with also that kind of ethnic diversity, were in places like Miami and Florida. Whereas you may know, South Florida has a very very, very diverse population, and especially because of the Caribbean and the history of movements, involuntary movement of populations, from slavery and all the legacies of those regions. There are many people with very, very diverse ethnic backgrounds. So it's very difficult for them to find a donor. And as soon as I landed there, we started doing transplants for children from their parents. At some of which I still, I see them now, and they're doing wonderfully. But their donors were just about passing the age to be considered possible donors. So we were lucky to reach there and be able to offer them those cures. And some of the patients who are whom we've cured, they come back and said they're committed to become blood disease specialists, and one of them is actually rotated in my lab and is now applying to medical school. So it's a full circle now.
It's just a multifaceted way of giving, good science and seeing what it created. It's just an amazing accomplishment. I would love to hear more about this. And we're going to turn it over to Ramana now for the next 15-20 minutes. He's going to talk about Nobel Prize winners. And you yourself are certainly right up there as one of the candidates. So let's take a listen. And I absolutely have enjoyed the segment, but we'll be right back for more.
Wonderful.
Absolutely. This is, we're all going to listen together. All and then after that, we can, actually, I may have came across your father, Asha, because I was a physicist, but I didn't practice physics. And I used to interact with a lot of Loyola and Northwestern Hospital radiation oncology physicists. There are quite a good number of friends. And I met a lot of Kerala people there. Most likely, I might have came across your father. I don't know. Yeah, but it is interesting.
He doesn't have the word retirement in his vocabulary, but we were able to get him to finally retire. And he went back to India and actually,
I love it.
Yeah, helped train about 40 plus of the physicists around the country now, who are now leading their cancer, efforts. So yeah.
Asha, a lot of people don't know that how physics is, because you're a daughter of a physicist, how much physics plays a role in all these researches and all these innovations. People don't understand how much. That's why if you see Jeff Bezos or Elon Musk, they are physics graduates. So I think physics plays a very mother of all sciences. I think it plays a very critical role in the future of cancer therapies and everything, in my view. So I'm going to present India's Nobel Prize winners. So one of those, actually, from neck of the woods of the Asha and me. I'm from Andhra Pradesh, so it's not that far. He's Tamil Nadu. His name is Sir Venkataraman Ramakrishnan. He was a sir. He was in Canada for a while, and then he moved to the United States, and then he became a professor in England. So then he got the Nobel Prize in the birthplace of Chidambaram, Tamil Nadu, and then they call him ribosome reader. I'm talking with God about the cells. Before Asha, I'm a physicist. I'm not a medical scientist. I wanted to remind that the little knowledge that I know, I can tell you about that. So they call him a ribosome reader. He was awarded Nobel Prize in 2009. The main thing was ribosome is the largest molecule, complex molecule. It reads the mRNA, messenger RNA. We talked about vaccines recently. Everybody is talking about mRNA vaccine. mRNA vaccine is a messenger RNA. It gives instructions, and the ribosome is the reader, and reads and produces the amino acids, and then eventually proteins are the high-tech coolies of our body. Actually high-tech and low-tech coolies of the body. So that is the ribosome reader. He what he did was he used a very complex mechanism to X-ray crystallography. X-ray crystallography is the one. Ribosome structure we don't know until he found out. He was instrumental in giving a complete ribosome structure. Is a very complex molecule. It is the life origins of life, because it repeats the is, if you don't mind, can you keep both of you mute button? If you can press the mute button, that is that will help us. Thank you so much, guys. So the Venkataraman, that's a ribosome molecule, is extremely complex. You see that on the left side. That's a folding in itself. Is a ribosome is RNA and protein is made up of RNA and protein, and it's a scanner. X-ray is a Xerox machine. It makes copies with the reads instruction, makes copies. That is the genesis of life itself. So he gave the complete description of the ribosome structure. That's why he won the Nobel Prize in 2009. The next one is from India. Is Aragobind Khurana. He's from Rajpur, British India. Is in Punjab. So what he did was oligonucleotides. He won the chemically manufactured genes. He's the first one in the 1968. He won the Nobel Prize in 1968. They call him father of genetic engineering. So he was oligonucleotides. So it was like a strands of the, I think, RNA. Asha can correct me if I'm wrong. The strands of RNA and DNA, they take it out and they ship it out. You can synthesize in the labs itself. Now the CRISPR is a clustered regulatory interspatial short palindromic repeats, which is a genetic gene editing tool. They use the gene editing tools to synthetic genes produce. So he was mentioned during the CRISPR genetic gene editing. His name was mentioned quite a bit. So he was awarded the Nobel Prize in 1968. He's truly remarkable in the beginning of the RNA DNA revolution. Aragobind Khurana, CRISPR is as I know, Asha went to the same schools, University of Stanford and Berkeley and San Francisco, University of San Francisco. That's where they found actually the two people awarded Nobel Prize recently from the UCSF. So this is the based on the research done by Aragobind Khurana. So that's a CRISPR. I can tell you about the CRISPR. Maybe there's a CRISPR is a gene editing tool. What it does is like a baby bacterial. A lot of people ask me, but very plain English. It is a baby mama bacteria. Takes the when it splits, before it splits into it, it gives you it gives you the bad dudes picture, which is the viruses or the bad dudes who are spoiling the yogurt. Actually, the yogurt manufacturer went to Berkeley and wanted to find out why some yogurts are going bad. So what they did was that Chobani actually is the company that they went to the UCSF and wanted to find out why some yogurts are getting bad using the same culture. So they found out that the viruses that present in those yogurt is messing around with this yogurt. But they found out some yogurts are not getting spoiled, some yogurts are getting spoiled. So what they found out is that it's just the mama bacteria, when they split into two, what it does is gives you the images of the viruses. It just stands of some kind of a strands, a genetic code implants into the baby bacteria, and then it also gives you a weapon, Cas9 scissors. And then when the baby bacteria sees the bad dude virus and goes and cut it in half. So Asha can talk about it. I'm talking about a plain low-level kind of talk this is. But
No,
anyway,
I think you said it beautifully. So, I think just to highlight one point, if you don't mind, Ramanaji. So,
yes,
see, there's a tie in here. So, if you look at the first individual you were describing, Gobind Khurana ji was actually given the Nobel long before the first
yes,
individual you're mentioning, right? And this was basically focused in genome and basically the gene signature and being able to target parts of the gene. The other individual was actually awarded focused on protein, making the genes, translating them into proteins. And then C.V. Raman well, you're going to come to him,
I'm
I'm
going
sure.
to talk about C.V.
Yeah.
Raman in a minute. I'm going to actually produce some small video on C.V. Raman. I did. So I'm going to show you in the C.V. Raman video. So yeah. So tell me about that a little bit. You're expanding. So the Aragovinda Khurana did the nucleotides. So a little bit about he found out the lab synthesized the genes in the lab, right? And the and the and the Ramakrishnan found out the actual ribosome structure and then
Correct.
produces the proteins that produce proteins. Is that right? If I'm
Correct. And
okay.
so you can see the tie-in, because when we talk about the genetic code or the code of life, there are many more subtle parts of life that we can't answer, but related to the genetic code, we know that DNA is essentially transcribed or made into a copy, a mirror image copy, or a matching complementary copy that's called RNA, which is part of what um, uh, Ramakrishna was doing. And then from there, that is taken to the ribosome, which was also part of his work, and translated to protein. And so it's this oligonucleotide sequencing that helped the understanding of how that code is translated. And there was an individual at Stanford who did a lot of work in that interface afterward named Paul Berg, who based his work on both of these scientists. So their work together was essential for that that sort of dissection of how all the proteins in our body are formed from the gene code.
Thank you. That's an excellent lesson from professor like you. We need it. So, but anyway, C.V. Raman. I'm going to play a video of C.V. Raman. I did a long time ago. So let me. That's
His name is Chandrasekhara Venkata Raman. He was born in Tiruchirappalli, state of Tamil Nadu, India. His name is long with numerous alphabets, but get used for it, because the next few decades belongs to this man. He is descending from heavens to destroy cancer. Just not cancer, he is omnipresent in every field: science, medicine, technology, engineering, and even theology. Welcome to the world of Raman gadgets. Raman probe. Point Raman probe to anyone and just click flash, just as you do on your phone. It gives instant result that person has a cancer or not. No elaborate testing, no other diagnostic testing required. Cancer detection in seconds. Raman pen. Raman pen, point and click at the finger and tell you the blood sugar levels instant. No more shedding of blood drops by millions of diabetic patients. Raman scanner. Just place your hand gently on the Formanex Raman scanner. It gives you the fruit and vegetable intake and in correlation with the antioxidant activity in your body. By monitoring antioxidant levels may help you to prevent some diseases. Raman inspector. Raman inspector, a handheld instrument, is an invaluable tool for law enforcement. Just point and click, it identifies the counterfeit drugs. Just point and click and can tell you it is a cocaine or any other illegal substance on the spot. No labs, no other testing required. Just point and click and can tell you right there if it is a hair gel or explosive material in the container without opening it. Raman reporter. Just point and click and instantly tell you if that is a true Picasso or not. No other verification required. This is done deal. It is just taught. Raman optical tweezers, Raman microscope, Raman TrueNarc, Raman imaging, Raman hyper, Raman transition, the list goes on. His name is truly omnipresent. This is not a science fiction. This is an extraordinary brilliance of a strikingly tall and dark handsome man from 19th century India. Hello, my name is Ramana Anamaraju and I have a passion for physics, specialized in allied healthcare and above all concern for all well-being of humanity. Sir Chandrasekhara Venkata Raman, usually referred as C.V. Raman, was born in 1888 near Chennai, India, and died in 1970. He discovered groundbreaking quantum phenomena in the field of optics while he was working as a professor of physics at University of Calcutta, India. He was knighted in 1929 by Queen of England and awarded Nobel Prize in 1930, first non-Caucasian ever to win in the field of science. His discovery is called Raman effect or Raman spectroscopy or Raman scattering, which are named after him. We only see objects, including people, when light falls on them and reflect back to our eye. But once in a while, the reflected light also gives stunning details about the molecular and atomic structure of the reflected matter, like a rotational and vibrational energies of the molecules or atoms. This unique reflection was discovered by C.V. Raman, and it is referred as a Raman scattering, along with few other names. With humans, Raman scattering gives exquisite details about the cell structure and its function like no other modality we ever seen before. Raman effect is the only way you can identify rotten apple from real ones without touching, smelling or cutting. This non-destructive method is unique to Raman discovery, so thus makes an invaluable tool in the field of medical diagnostics without exposure to any radiation. A perfect tool for law enforcement without opening containers to check for explosives. A perfect method to check the authenticity of the age-old art without using any chemicals. Raman scattering analyzes vibrational and rotational spectra of the target material by using a non-destructive method. Cancer. At present, one of the most advanced methods of detecting cancer is through positron emission tomography, referred as a PET scan. This highly expensive and complicated equipment occupies 10,000 square foot office building or placed on 18-wheelers. The average cost for this procedure is around $4,000. Imagine exam that combines into a single scan the diagnostic imaging power of 10 PET studies, each measuring an essential dimension of cancer's aggressiveness, metastatic potential, and susceptibility to the radio and chemotherapy at the cost less than $25. Raman spectrometer, handheld Raman spectrometer can deliver that punch with a style. By attaching gold nanoparticles to the cancer cells, Raman spectrometer hunts every one of the cancer cells, identifies them, and kills them with a nano-heated guided missiles. Well-respected magazine Diagnostic Imaging describes Raman spectroscopy, a quantum physics technique puts all preceding medical imaging modalities to shame. Raman, the cancer avenger, descended from heavens to rescue mankind from this fatal disease. Raman puts cancer detection is at our fingertips, figuratively and literally. C.V. Raman may be Hindu, but his discovery recanted the rituals in the church that happened centuries ago during early Christianity with stunning details. Santorio delle Peregrina, 13th century historical church sitting near a beautiful Cantabrian mountains in Spain. The church completely lost its original Romanesque mudajja or brick architecture through centuries of rituals and tourism. It is impossible to recreate the original architecture with all its colors and beauty since there was no historical data available. Raman spectroscopy came as a surprise savior for the church. Raman spectroscopy took layer by layer the centuries of environmental destruction, the dust left by oil lamps in 13th century rituals, natural decay of the bricks. Raman spectroscopy brought back the original image of the architecture with the stunning details. In recent years, 13th century Pilgrim Church was remodeled to its original architecture with all its beauty and grandeur. Thanks to Sir Chandrasekhara Venkata Raman, a true scientist and a true patriot of India. In the field of medicine, Raman spectroscopy coming with a true revolution. You can literally test for cancer with the handheld instruments at primary care offices or even at a boutique drugstores in coming years. By catching the disease such an early stage dramatically reduces the cost of this fatal disease. A man from heaven gave a remarkable gift to humans. I am proud to share part of his name. Thank you for listening.
I'm teaching the English to English professor, Asha. So
No,
I
that's
never really thought
wonderfully,
that we can
wonderfully
add all those
summarized.
things.
You no, you summarized it wonderfully. I just want to add one more point there.
Yes.
So really, so C.V. Raman's work was the basis for the methods of X-ray crystallography, which really is a way to look at molecules. I mean, now we have even more advanced ways, but they were all developed out of that technique, and um, that is what was used to discover the structure of DNA, the
Mm.
structure of RNA, and the work of Dr. Ramachandran, which was the first individual um, that Ramanuji was talking about. And incidentally, he's well regarded. Ramachandran, the first
I'm
person.
going to talk about him actually in a second.
Yeah, he actually wasn't awarded the Nobel Prize. He was
He was a
nominated.
nominee. I put a
Yeah,
nominees also there. Yeah, that I did.
right, right.
Oh, very good. So I actually is in right now is Raman spectroscopy is in the Sherlock, is in the Mars Perseverance rover because they're looking for life. It's called Sherlock, is scanning habitable luminescence for organic chemicals. The scanning habitable Raman actually scanning habitable Raman spectroscopy is using right now. They're using in the Mars to detect the life in the Mars planet. That's one of the things is it really still is playing a role. But let me talk about the other one. Then second one is the next one is Subramanyam Chandrasekhar. He is from Chicago. He was at University of Chicago. He won the Nobel Prize in 1983 for the black holes study of black holes. The black holes are, as you all know, that when you have a mass is such a big, what is the Chandrasekhar limit? He created a Chandrasekhar limit, so the amount of the mass, critical mass that is needed to collapse a mass into black hole, that's what they call Chandrasekhar limit. He did extensive work on the black holes. So he was awarded in 1983. He was born in Lahore in Pakistan right now because his father was a diplomat there. So he was born Chandrasekhar. He recently died, but Subramanian Chandrasekhar awarded Nobel Prize in 1983 on the black hole physics. The next one I'm going to talk about Subramaniam Chandrasekhar, the NASA awarded a Chandra, they created a Chandra X-ray observatory because electromagnetic spectrum is a gamma rays, all you have a beta rays, microwave, radio waves, all of the complete electromagnetic spectrum. X-ray is one of them. So you can study quasars and the neutron stars. They release X-rays. So you can measure the X-rays through Chandra X-ray laboratory. So it was a very important one. So they named after him. Chandra is the part of his name. Subramanian Chandrasekhar. NASA named after him. That is the Chandra's X-ray. Is playing a very critical role in that one. The next one is that people don't know about him. He's born in India. Is a Dr. Ronald Ross. Is a Nobel Prize winner in 1902. Birthplace is almost Uttarakhand, and he spent all his life in India, in my hometown Visakhapatnam, and then he went to Calcutta, and then he was awarded in 1902 Nobel Prize because that he discovered the transmission of malaria parasitic infection through the birds, through the malaria and birds, the malaria. So that's why he awarded. Actually, his name is still is a British citizen originally, but he's lived in most of his life in India. Is a malaria actually in Assam. There is a tea hospital in the all his work is displayed right now. You can go to in Calcutta. There is a memorial also. So he awarded Nobel Prize. So not too many people know he was born in India and grew up in India. So the next one, C.V. Raman, I already spoke about it. Now I'm going to talk about notable nominees of Indian. So Sachindranath Bose was born in Calcutta, India. Bose, he was credited for the Bose-Einstein condensate. Bose-Einstein condensate is the fifth state of matter. Solid, liquid, gas, and plasma. The fifth state of matter is called Bose-Einstein condensate. It's as peculiar as it is a peculiar state. It is when you cool the water to all the way to the absolute, close to the absolute zero temperatures, what it becomes a Bose-Einstein condensate. It's a very strange material. So if the light passes through it, it brings the speed of light is 186,000 miles per second. almost. That brings the grinding halt. This material brings the photons to the grinding halt almost. You can almost pick up the hand in that much. It slows down the speed of light, the photon speed. So he was a Bose gave the mathematical structure for that. He sent it this the reason they call Bose-Einstein condensate, because he sent a letter to the Einstein, because nobody paid attention to him. The bosons, they are the particles in the part of the bosons are the fundamental the bosons and fermions are the constituents of the entire universe. Though these are the bosons are the particularly they're like friends. They're very close friends. They can stay in the same state. I don't want to get into too much physics, but Bose Einstein condensate. He sent it to Einstein. Einstein rewrote a little bit and then published it in the German newspaper before he moved to the United States. So Bose Einstein condensate was actually after 75 years after his death in the University of Colorado, they produced the first Bose Einstein condensate material. He didn't know that they produced it. They won the Nobel Prize, all three. One of them won 3 Nobel Prizes. There are 10 Nobel Prizes awarded. The relation to the Bose-Einstein condensate. Those 7 Higgs boson, actually, Sachindranath Bose went to Europe. He was working with Paul Dirac, made him Madame Curie, and then Niels Bohr. He attended classes in Niels Bohr, and he was very active in the physics area in the Europe. So he went to then. That's why Paul Dirac, one of the very well respected, I did a PET CT scan on the most beautiful equation in medicine by Paul Dirac. So he actually named the Higgs boson, the God's particle, named after him. Boson, his name came from Bose, Sachindranath Bose. So that is the name of the origination. The name is Sachindranath Bose. So he was nominated for the Nobel Prize, but he did not win the Nobel Prize. He died, 1970s. He died. The next is Jagadish Chandra Bose. He was work in the previous India, the British India. He was born in Dhaka. He was he's a polymath. He's the first polymath of India. Physics, biology, astronomy. He did a physiology of the plants. And then Wi-Fi is one of the original inventor of the Wi-Fi kind of things. He found out first semiconductors. That they were the conducting electricity. They were thinking about first the iron fillings. Then they started doing these crystals. He is the first one who used a crystal kind of thing, the diodes that used in the transmission of the electricity. That's why he is a kind of a beginning of the. He contributed quite a bit to the semiconductor physics, and then he is also met the Marconi. They were working at the same time in the Wi-Fi. The radio waves together. So that is a Marconi. He met Marconi in Italy, Italian Guglielmo Marconi. They worked together, but they didn't work together. They actually doing the same research. But Jagadish Chandra Bose research really from the semiconductor physics. The next one, she's talking about G.N. Ramachandran. She can talk about him a little bit. He was born in Ernakulam, India, Kerala. That's where Asha is born, I think. She can talk about it. Ramachandran, we use in physics, they used to call him Madras Group. He moved to the Madras University eventually. He was he was actually an Indian Institute of Sciences, where my brother's friend used to work there. Is a Palakoredi Sharma. He was a colleague in that sense. The Madras. Then he moved to Madras, Chennai. He was born in Kerala, but he moved to a different city. It's a big university. Madras is a much more popular one. They did the Ramachandran plot to understand the structure of the with the X-ray crystallography. They know a little bit about at that time. Actually, used X-rays to find out the particularly protein structures, conformity, because we have a problem with the 3-dimensional structures. It's very hard to find these. So you need to use a lot of mathematics. It's called a Ramachandran plot. They still use the Ramachandran plot to find out the. So Asha can add a little bit anything to Ramachandran.
Yeah, I'll just add one very interesting point. So for the lay individuals who might be listening to this, everyone knows about collagen.
Mhm.
Collagen is sort of one of the central building blocks, and everyone uses it in, preservation of the skin. It's central to the cartilage, and he actually discovered the structure of collagen.
Oh, I
So,
didn't
That's
know that.
fascinating.
yes.
I should add that next time. Collagen
Yeah.
discovery that he did that. I didn't know that. Yeah, that is a truly remarkable. He was nominated for the Nobel Prize. He should have got it. There is a lot of times a lot of Nobel Prize was not that fair at the time. So the next one is George Sudarshan, another guy from Kerala, Pallam, Kerala. So he's University of Austin, Texas. He retired. Probably that Asha's father may know him.
He's a friend of my
He's
father. I actually used to call him
Oh,
uncle. I used to call him uncle. Yes, exactly.
yeah, he,
oh my
he is
goodness. Yeah.
yeah, he's University of Texas. He was nominated for the Nobel Prize. He was tachyons of the faster than there was a. These are the phantom particles. They give a mathematical structures for the things that particles that can go faster than speed of light. Einstein is different with Einstein. So you predicted that there are particles because quantum entanglement is one of the concepts that is a problem, and he came up with a mathematical structure of the tachyons which can go faster than fast speed of light because tachyon field is a pervading universal field, so it is there here all over the places. So he was inventor. Still they think that it's possible that some of the fields still did ongoing research. In the is of one of the particles, a photon goes one photon goes faster than light, other photon goes slower than light. So these combinations, they're still thinking is of some of the physics that we have, quantum gravity and all those things. We are having a problem. George Sturgeon gave a lot of mathematical structures, well respected in the physics. So Asha may know personally. He knows she said that. She can add a little bit more to. He's the University of Texas, so Austin. He died recently. He died in 2018. In fact, is the last of all the Nobel Prize winners and nominees. All of them died. Is recently when I was making this video, this presentation, he was alive. Still, he
Wow.
recently died 2018. But tell me a little bit about Asha. You're a physics and a cancer specialist. You're the only one I know.
I think you summarized it well. There was a lot of controversy around his not being, receiving the Nobel. And in fact, the Swedish Academy and several international scientists protested in his name because of the relevance of his work. And all of the nominees that you're describing, Nirmalaji, these are very, very fundamental, very broad impact discoveries that were made, and it kind of speaks to the issues of the geopolitics around all things in the world related to recognition, etc. What's going on in the discussions around equity, etc. But these scientists were so dedicated to their field that they just, they didn't
It's
they
an
didn't fight
amazing.
anything. Yeah.
They didn't
But
care, did they? They just forged forward.
yeah, the next one is a sad case. Homi Baba, she is talking about her
Yes.
father used to work for her. Homi Baba birthplace was Bombay. He's a Parsi. He came from a very, very wealthy family. Tata fundamental research is a Tata family. Tata family, they did a lot of research. He is one of the, I got for Tata Fundamental Research Institute. He was instrumental in founding the Tata Fundamental Institute, Research Institute. He is also born in Bombay, India. Then he went to Cambridge, actually, he went to school there, and then he got the Nuclear Newton Fellowship. Very few people got the Isaac Newton Fellowship. He got the Isaac Newton Scholarship. He studied in the Cambridge. Then he worked on the most of the work, his work is on the cosmic rays and then he's a very administrator too, a great administrator. He's a Baba Atomic Research Institute, the nuclear center nuclear physics that started. Actually, I got a job there. I didn't take it. I came to, that's one of the mistakes I made probably, I think. But I came back to the United States. But I got the job offer from Bach. At the time he was the inventor of he did a lot of work on the cosmic rays. Cosmic rays are coming from the on the birth of some of these mysterious rays at the time. These are the traveling for $10 billion at the beginning of the universe from quasars and neutron stars and the black holes. So these are all coming from outside of the black holes. These are all coming from the cosmic rays. He was excellent in studying the Wilson chamber and all those things. So his Homi Baba was. So I saw recently. Asha was talking about his death. So, Asha, you can expand on that one a little bit.
Yes, so I'll be brief again. I have an actual photo. I had to recently give a talk at Baba Atomic Research Center, and it was ironic because I literally was conceived there, and I was raised there for a period of time when my father was in that first batch of students under Homi Baba, but I was born much after that. But his center was sort of the place where all of these great activities of all the major physicists of India at that time were being done. And so I have a photo of my father as a young 18 to 19-year-old in that first batch of Indians, young men selected from all around the country. To come and be part of a very important set of projects for New India at that time, which was nuclear energy and radiation safety and cancer and all these other aspects of what he was trying to do with the nuclear programs for the country. And Homi Baba had a vision that was part of a larger vision of many statesmen of that time, which was the space program and the nuclear energy programs of the country. And so this was there's a lot of controversy around what happened, and I refer you to what I had posted as well as the things that can be readily found on the internet now. There were, as you know, at that time in the 1960s, there were a lot of very unusual situations in which major statesmen from other countries outside of the United States, even within the United States, were disappearing or being killed, etc. And he was invited to speak at a major conference and to meet with the Atomic Energy Commission of Europe. And in that process of flying out there, his flight had a very inexplicable mishap. You have to read the details to understand it. And he was essentially, he died in that crash along with all the other people in the plane. And this was the end for a period of several decades of the forward momentum of the space and nuclear programs of India, which were, as you can see from the history of the science, were in a different plane in terms of where they were going. So they were the major competitors to the United States, actually, despite the fact that economically they had been ravaged by colonialism. But so the summary is that that was a huge setback to generations of scientists from India, and yet they pushed forward. So people like Ramanaji and all these who have come, physics was such a central part of the scientific inquiry. Physics, mathematics, and astronomy and astro studies. So these areas from, imagine we're talking about the smallest molecules, nucleotides, that are the genetic code, to the largest objects in the universe were being studied simultaneously across much of the Indian subcontinent. And Homi Baba was trying to harness the youth of the country for a mission that was really quite grand. So in any case, I think it was a great blow to the scientists as a whole in the country that he was assassinated. And that's
I didn't know
exactly.
that he died in a plane crash. After reading
Yeah.
that, I was surprised. Thank you
Yeah.
for letting me know that. But the next one is a more fascinating, Asha. He is from my hometown. Yeah, but nobody knows about him.
I'm
But
actually writing a book on him.
you're writing a book on him. Oh my
Yes,
God.
on Yellapudi Subbarao.
Yellowpegada
Correct.
Subbarao.
Yes.
He has done an amazing job, and he was saved me personally because I don't know him. My father's name is Subbarao too. We are from the same town. We went to the same temple, same streets, but he's died even before my father was born. He died
Really?
in 1948. He died. Um, it is as for no methotrexate, the cancer drug. He invented the cancer drug. He did a strip test of the phosphor in Harvard, and he had us on tablets. That's why I took it and saved me the tropical diseases. Iromycin, broad spectrum antibiotic. He did all of them. He found it, and he didn't get the single Nobel Prize. That was a very, as you said, the George Sudarshan, Homi Baba. They're all rejected. These are all G.N. Ramachandran. They truly deserve it, and this guy is a particularly deserve it with the 4 discoveries, the major discoveries. He did that. You can add a little bit, Asha, because I did a special show on him. He's from my
Okay, I'll keep
hometown.
it.
He's from my
I'll keep
village,
it.
my
I'll keep
farm.
it. Okay, I'll keep it very brief.
Yeah,
There's a very important other fact about him. Actually, if you know about the molecule called ATP, adenosine
yeah. ADP,
triphosphate,
yes.
all energy,
Yeah,
all energy in living beings
correct.
depends on this one molecule. And methotrexate, the discovery of this most central, we methotrexate is regularly used for all cancers, in many different cancers, as well as in transplantation still. Um, these fundamental discoveries were made by him, and it was a side effect of the discovery of ATP. This gentleman was actually the basis for the founding of Dana-Farber Cancer Institute, because the person who used most of those findings to move forward in the field of cancer
It's,
treatment was
yeah.
in the same research space as him. And that's how, there are major
Did you change anything in our microphone? Your microphone is changing different a little bit.
I'm sorry, can you hear me now?
Yeah.
A little bit better.
Yeah.
Oh, I'm so sorry.
Before
Oh,
now
that's
it's better.
better.
Yeah, that's
Okay.
better.
Yeah, did you repeat, or was it clear already?
So, yeah, you were talking about ATP, and really the side effect of it being his
Okay.
discovery,
Right.
and amazingly the start of Dana-Farber. Is that what you were
Right.
saying?
Right. So when you discover ATP, you start realizing about how certain nucleotides, which are basically the basic building blocks of the gene code, are metabolized in cells.
Can you adjust your microphone? Something changed it in a minute ago. I don't know what happened was.
Let's see if is it clearer
Yeah,
now?
now. You talk, yeah, say something.
Yes.
Is it clearer now?
Yeah, perfect.
It looks like there's a streaming problem, but let's hope it. So when you discover the molecule that's responsible for energy storage, it's a form of one of these metabolites or products inside the cell, and that is actually the basis for how methotrexate functions. It functions in the recycling of these molecules.
Right.
So it's actually a side effect of his work that this even methotrexate. Can you imagine that just the offshoot of one of his discoveries was responsible for one of the major cancer treatments of the century?
Yeah, it is. It's truly
Incredibly
remarkable.
broad impact.
I'm glad you're writing a book. Is
Yes, I want to hear about that on our next show, right?
Yeah, yes.
Kind of running out of time now, but yes,
Yes,
me
my
luck. I'm
hometown
working on
hero. My hometown hero. He is in anyway. That's next. I'm going to talk about the Nobel prizes by country. United States is a 400. 400. We're not even catching up. The rest of the world is very, very far behind it. So India is not even a top 10. Some extent, is a discrimination is also involved. Let me introduce you mathematics part of it. Mathematics is as important as physics. So there are two Indian mathematicians who got the field medals, which is equivalent to the Nobel Prize. Ashke Venkatesh, she's recently got the Nobel Prize and the Manjul Bhargav, whom I met in Princeton. One day I'm going to the coffee in Princeton campus. I went with my friend. We were walking around in the Princeton campus. This a kid-looking guy came to me and I asked him, "Where is the Starbucks?" Wrapping up soon, yeah. The yeah. So that is a Manjul field medals or the Ashke Venkatesh and Manjul Bhargav. They worked on a lot of number theory on the based on the most of them are Ramanujan's work. Srinivasa Ramanujan's work. Let me move to the next one. These are the two invitations. The next one is very interesting. I don't want to forget our Persian woman here, Iranian woman here. So this is it's a Sheila Dolashahi. Dolashahi is from Iran. So this is the one I wanted to mention about Mariam Mirza. Mariam Mirzakhani is a professor at the Stanford. The first woman received a mathematics field medal for the first woman. That's an amazing, in fact. What she did was the Secrets of the Surfaces. There is a movie, it's called Secrets of the Surfaces. You should watch that movie. Is a Kumaran Wafa is one of the physicists from Harvard, and he brought her, actually helped her to come down here, and she did extensive work. He didn't. Kumaran Wafa probably was a nominee. Nominees, they won't disclose you until they're 50 years passing, they won't disclose. So we don't know whether he was nominated, but I'm pretty sure he was nominated. Kumaran Wafa is a Harvard physicist. So he brought her to Harvard, and then she came, and then Mariam came down and did extensive research on the surfaces of the physics secret of the surfaces. If you see, I'm giving you very layman description. If you see a glass, that is the surface tension. If you see that how the surface tension moves with the area of the glass increases decreases. So it's very interesting concept. Dynamic surfacing, this called the dynamic surfaces. So they did these are the angels and demons of this is by Escher, the artist, that's what the mathematicians study about the secret surfaces, because we need a string theory. There's only three dimensions are there. So if you want to put on a higher dimensions, for example, I didn't tell you about this, that's oranges I put there. If you put an orange stack, that is you can do, it's the biggest problem for orange stacking problem, is the biggest problem in physics and mathematics. How many oranges you can fit in with the maximizing the space. That's the biggest study. Then the biggest study came in after that is how many oranges you can put in the higher dimensions after three. If there are 11 dimensions, how you can put the oranges in those kind of dimensions. So that's why they do higher dimensional surfaces. So Maria Mirzakhani is a very important instrument in the string theory. She gave a life to a string theory when it was dying. So she's a truly inspiring woman. And unfortunately, she died at the age of 40 with the breast cancer. Tell me about Asha. She just prime age of 40. She died. It's a very sad story. So now we talk about the talk about that. Let me talk about the cancers and all those things. Let me so think about that, Asha. People at the age of 40, she died with a cancer. She's a Stanford professor. We have any solutions is coming up? We think we're going to solve this cancer problem? It is such a devastating situation we have.
Yeah, we have two problems related to cancer. Obviously, a lot of problems, but if I were to summarize them, obviously we need better, less toxic, and yet more efficacious or effective therapies, right, to cure, not just to treat, but to cure it. And secondly, the incidence of cancer and the types of cancer are getting worse, actually. And so this has to do with lifestyle and exposures and all of the other things that we're talking about, as well as possibly changes that are happening, mutational changes in our bodies related to the lifestyles of a globalized economy in which you don't know where your food has come from, your water is coming from, et cetera, et cetera. So let me focus on the first. When I joined Stanford in 2000, I actually, many of the stalwarts, the big names in the field were my professors. I used to constantly ask the question, which they allowed me to pursue, and some of us have continued doing, and some of my mentors since then have all been active in this, which is, why would you give a toxin to treat the cancer, knowing that it affects the immune system that's needed to remove the cancer, to fight the cancer? And no one had a really good explanation for that, excepting that this was the field, and they had a lot of explanations that were historical. So remember that when a patient got relapse or their disease came back, they would get more aggressive chemotherapy, which was completely counterintuitive to me, because you're destroying the immune system, and not surprisingly, a lot of people would just get worse as you continued hitting them with more and more, and their quality of life just became abysmal. And so we're immunotherapy, removing
If you
all
come close, Asha, if you can come close to the mic a little bit
removing
better,
these
and then don't
toxins.
move too much, because
Okay,
my audio is becoming a little bit of a
so sorry.
challenge.
Is it clear now?
Yes.
Yeah,
Okay, so removing these toxins is so important to the process. And trying to allow the immune system itself, which normally prevents cancer, while we've been doing this broadcast, each of us has had cells that have gone cancerous and been killed, been cleared by our immune systems. And so it's so important to realize the power of that system. And in fact, that's what we're showing now with the therapies, and we're helping to develop those in Regeneron and in many places, that harnessing the immune system is going to be the key to eradicating cancer. The reason is because millions of years of evolution have said so that these cells can detect the errors in their own cells, much like the Navy SEALs I talked about. It takes a Navy SEAL to do that. So I think that's going to be the future of cancer therapy. among other things. When you ask for more specific things, what we have to start doing is being able to take a person's individual cancer and see what is abnormal about that can be targeted. Then use that patient's immune system or another healthy person's immune system to target that. And I believe that that's going to be the future of really curing cancer in our
But
life.
Asha, I have one question for you. I'm a physicist, you're a daughter of a physicist. You are. We don't believe in, when doctors say that to me, oh, there's a no cancer is same. Every cancer is different. That's a problem for me because unified field theory origins must be the same in physics. Yeah, all the forces, natural forces, has to be same. So there must be one particular common thread, a common cause. That's a source has to come from all these cancers. What is that? Do we know that, or we are
We
still
don't
far
know.
away
We don't
from
know
that?
that. We don't know that. And personally, I doubt that it is a single thing. And the reason I believe that is, remember that what's unique about cancer as compared to other diseases, can you hear me okay?
Yeah,
It's not localized to one part of the body, not just in terms of spread. So a liver cancer and a type of liver cancer can be very, very different than a brain cancer. And this because these tissues have very different genetic operation outside of the gene code. It's correct, and you can say that the entire genes of the person are the same in their brain and in their liver, but they're not. Because this is why liver tissue behaves like liver tissue, not like brain tissue, and vice versa. Right? Now, that doesn't mean we couldn't get to that point, and it would be a nice, exciting theoretical point to be able to simplify. But the reality of the disease isn't like that. For those of us who have literally held hundreds of people in our hands, as you know, as they deal with the disease, it's a very diverse disease. So diabetes is one disease, correct? High blood pressure is one disease, even though it affects the whole body. But cancer is not one disease, not at all. And in fact, childhood cancer is even very different in the same tissue than adult cancer in the same tissue. So I think that that's going to be a very big shift in the understanding. I just want to point out that until just even now, last year in our pediatric cancer ward, a child that gets a sarcoma, a cancer of their muscle, has a horrific set of chemotherapy for 3 years in which they destroy their immune systems, and we expect them to survive from this. It's completely counterintuitive. And it's actually counter scientific in my view. And so I think where we have to move is um, using, we could call it holistic, but empowering the immune system, whether it's the own patient's immune system or being able to take off the shelf cells, like off the shelf chemotherapy, and treat it.
Usually I don't extend one more than an hour, but they're
I know,
wonderful.
I'm so sorry we're
I
late.
love to talk with you. One more thing I wanted to ask you. Mirzakhani died, at the age of 40. Both your woman up here. Breast cancer is the biggest threat to the womanhood. How are we progressing anything? Are
Yes.
we?
So,
Yeah. So tell me something about breast cancer.
so
Progress in breast cancer.
Yeah, there are some restrictions I have on what I can speak about publicly, but let me speak about. So I will say that I have a particular interest, and I think we need to focus in a few specific diseases that are just so prevalent and very poorly understood. Breast cancer, ovarian cancer, gynecologic malignancies are extremely poorly understood, and liver cancers and these are all very prevalent globally. These really need a lot more investigation. Now, in breast cancer, what's really unique is this is a tissue that normally is exposed to a lot of blood flow and, milk, breast milk is expressed through that organ, and so much immunity happens in that organ because that's how a baby that's breastfed actually gains its first immunity. Breastfed babies have a very different healthy immune environment compared to non-breastfed babies, and so, when the breast develops a cancer, depending where it's located, it has a remarkable ability to camouflage itself, the cancer itself, to look like normal healthy tissue and evade immune detection. And that's the key, is we're trying to make the tumor become recognizable to the immune system.
So a lot of calcifications also look like a that's a I was working with them. I used to own an imaging center when we were doing mammograms. For example, there is a lot of calcifications. They're very very
Very deceptive.
very
Yes.
deceptive in that process. So I mean, we are using a lot of entropy mathematics to detect the progression of that how it does the disorderliness of the cancer. But I'm so excited about this. Cancer is a really threat to the humanity. We need to solve the problem. The moonshot, they're talking about moonshot. Are they? I hope that you're giving us a hope that there is a lot of things progressing, Asha.
Yes.
Really, truly, it is an honor. It is a privilege to talk with you. It is a totally interesting. I have a very rare combination of physicist daughter and a lot of exposure to the physics and physics my idols, and the cancer itself. We are in the forefront of the cancer therapies. You're inventor. I'm a truly honored. Sheila, do you want to any closing
It's been
thoughts?
incredible, and I truly look forward to having Romana come back and put you on one of the slides and your name for your impact in cancer treatment. So thank you
Which is
for the work that you're doing, and we wish you the very, very best in your
Thank
endeavors
you so
at
much.
Regeneron. Thank
We
you.
need your good wishes. So wish us all the best and good luck so that we can continue to do something useful for society.
Absolutely.
Thank you.
You
Thank you
already
all.
have,
Thank
but
you for
thank you.
doing
We
this.
thank you so
Wonderful to
much.
meet with you all. And Ramana, I'll tell my father about you. We have to connect you both.
Yeah, we're gonna. Yeah,
And
thank you.
I look forward to working with you in the future, Sheila, on
Oh,
something.
yes, absolutely. Thank you. Take
All the
Thank
care.
best.
you.
Thank
Have a
you.
great night.
We are retelling their stories through our patented designs that can be worn on scrubs, t-shirts, printed on conference bags, and endless other promotional materials. Daily Wear for Medicine is the first ever of its kind to create curiosity in medicine through visual art. We at MedBricks are celebrating unsung heroes of the past who made enormous contributions to the field of medicine through our unique campaign called Daily Wear for Medicine. You can wear it, carry it, and give it.